Hello everyone, I am Sweta and I will be presenting our work Unsupervised Discriminative Embedding for Subaction Learning in Complex Activities. This work is in collaboration with Dr. Hilde from MIT IBM Watson Lab and Dr. Yogesh Rawat and Professor Mubarak Shah from CRCV UCF. And this work has been sponsored by DARPA. So first let's look at a complex activity. A complex activity is composed of a sequence of subactions. Here we show a video of a person performing the activity make cereals. Here and in this video you would notice that the person is performing the subactions pour cereals into a bowl, pour milk and stir cereals. It is interesting to note that in a complex activity there can be variation in the ordering of subactions as well as variation in the duration of the subactions based on the person performing the task. The problem we are interested in solving is temporal detection and segmentation of subactions for a complex activity. That is, for example, here we show sample frames from a complex activity video where we show highlight frames which depicts the subaction happening like pour cereals, pour milk and stir cereals, and the bar plots would represent the temporal order of frames for that video, and we are interested in segmenting the subactions temporally in that video. Most of the complex activities are long range and getting annotations for them is time consuming and challenging in practice, especially to obtain frame level annotation. It is very expensive and not scalable in terms of data size. So, to address this, our goal is to develop an unsupervised method which does not require these frame level annotations to reason about the subactions for the complex activity. So, the challenges in this setting would be first to break down a complex activity into semantically meaningful subactions and then capture the temporal relationship between these subactions. The prior works in this literature mostly focus on two-stage approaches where in stage 1 they perform an embedding learning based on visual and or a temporal representation, and in stage 2 they perform an explicit clustering step learned on the embedding in stage 1. By making the clustering step independent of embedding learning, the overall approach becomes suboptimal. We try to address these aspects in our work and come up with the following contributions. So, we propose an unsupervised end-to-end approach where we propose a joint learning mechanism that simultaneously incorporates visual and temporal information, and then to better learn the spatiotemporal representation we propose to use temporal positional encoding based on inspired by the transformers. And then we propose a novel latent discriminative concept learning module. With the help of contrastive laws, we integrate clustering as part of latent embedding learning. Now, let us look into the notation before delving into the model architecture. So, given n videos where each video is represented by mn features, we denote xnm as the mth feature in nth video and its corresponding positional encoding vector by rho nm. The goal is to learn the subactions and the ordering for subactivity. For that, we would predict a subaction label for each feature vector in each video. So, now let us look into the model for the details. So, given input videos which is then passed to the I3D network to compute visual features xnm, and then passed to the positional encoding branch to compute the positional encoding vectors for each clip which is denoted by rho nm. So, the xnm is passed to the encoder which is then fused with the positional encoding vectors with the help of an FC to generate a representation phi nm. And then with the help of an attention block we learn the latent concepts which is called as y hat, and then with the help of an MLP which takes in as an input a randomly initialized latent vector nodes y1 to yk as shown in the block A. For each input vector phi nm, with the help of an attention block and latent concept, we generate a representation znm in the latent space such that each znm gets assigned to one of the latent concepts. And with the help of contrastive laws, we perform a grouping such that all the similar clips get assigned to one latent concept and it is pushed far away from all the other latent concepts. Once we have learned this representation, we again decompose it into visual and temporal information. And to generate the visual feature representation, we pass it through a decoder with skip connection to generate x prime nm. And to generate the temporal position encoding vector, we pass it through an FC to reconstruct that information. To train the encoder decoder model, we use a reconstruction loss over the generated representations for visual as well as temporal information as shown here. Now, let us look into the overall pipeline of our approach. Given input videos, our model learns a latent space such that the latent concepts can be associated to semantically meaningful subactions within an activity, and here we color code the latent concepts to have it assigned to one of the subactivity in the activity make chocolate milk. For example, the latent concept which is highlighted as green represents the subaction pour milk, and the latent concept that is shown as pink represents the subaction stir milk. Once we have this learned latent representation, we can generate the initial predictions from the model. So, to do this, what we do is for each feature vector representation, based on which latent concept it gets assigned to, based on the similarity of it, we can generate the prediction for it. And we arrange all the clips based on the predictions as per the initial sequence to generate the initial predictions for the video. As you can see, there are slight jitters that are happening whenever there is a transition from one subaction to another. So, to do that, we use Viterbi to refine the temporal ordering and generate the final predictions. As you can see, these jitters are then reduced with the help of Viterbi, and here we show a comparison of our initial predictions, final predictions, and the ground truth for a sample video. So, now let us look a little bit deeper into how we perform our Viterbi decoding. Once we have this latent space learned, we can generate the initial predictions, and we define a transition modeling for the latent concepts with the help of the latent clips that are assigned to it. We compute a mean time for each latent concept based on the mean of all the timestamps of the clips assigned to it, and use that to define the ordering of these latent concepts. So, if T1 is the mean time for Y1 and T5 is the mean time for Y5, then if T1 is less than T5, then we say that the subaction take up occurs before the subaction take at T back, and we use this strict ordering of state transition and refine the initial predictions to generate final predictions with the help of Viterbi. Now, let us look at the results. We show results on 3 benchmark data sets. First, we show results on breakfast data set, which has 10 activities, mostly in the cooking, performing cooking activities. So, we compare with weekly supervised state of the art and unsupervised state of the art. We show that our approach outperforms the state of the art F1 score by 2% with a competitive mean over frame accuracy. Additionally, apart from evaluating our method for the task of subaction learning, we also evaluate it for the task of unsupervised event segmentation, where the goal is to identify the boundaries for the subactions, and we show that our method outperforms the state of the art unsupervised event segmentation method by like a whooping 30% improvement. So, next we present our results on 50 salads data set. So, 50 salads data set is composed of videos performing the activity making mixed salad, and we use RGB frames in this in our work to report our results. So, we compare with unsupervised approaches that report around 35.5% and 30% mean over frame accuracy, while our method generates around 42.2%, which is like 7% improvement over state of the art with a 34.4% F1 score. And for the task of unsupervised event segmentation, we show 10% improvement over the state of the art. In the next data set we report our results is YouTube instruction data set. This data set is different from the previous two, as in this data set it is not restricted to a kitchen setting, but it has more general activities like changing a car tire, performing CPR, or repotting a plant. And these videos are directly taken from a YouTube video like YouTube. So, there is no recipe given to participants, and it is slightly challenging compared to the other data sets. So, here are the unsupervised state of the art approaches which report results on YouTube instruction data set, and we show that our method with a competitive F1 score shows 4% improvement over state of the art, indicating that our method also works well in a generic setting where there is no recipe given to a participant, but it is still able to model the relationships. Even for the task of unsupervised event segmentation, our method shows like around 6% improvement over state of the art, indicating the robustness of our approach for this task. Now, to show that the improvement or gain in performance is not just about better features, we show a comparison of baseline with the same feature space. For that, since the baseline is trained with Fisher vectors, we train the baseline with I3D features and report the results, and compares our model, which is also trained on I3D, to show that the gain in performance is because of the model's capability to handle robust representations, and it is able to generate better feature space. And then we analyze the role of positional encoding and skip connections to model the latent representations. So, if we remove the positional encoding branch, then it reports an overall accuracy of 40.9% with an F1 score of 20%, indicating that positional encoding plays a important role in modeling the representation. When we remove the skip connections, we see that the MOC decreases to 35.7% with an F1 score of 28%. This indicates that having skip connection helps in modeling the generality of an action, and that leads to help in modeling better latent representations. And having both of them definitely leads to a better performance, which is 46.9% accuracy and 31 with a 31.9% F1 score. Next, we analyze the role of individual loss components which impact the overall performance. So, we have two main loss components, one is the reconstruction loss and next is the contrastive loss. And reconstruction loss is further divided into visual feature reconstruction and positional encoding reconstruction. The top part of the table focuses on reconstruction loss and is trained without contrastive loss. As it can be seen that just using visual feature reconstruction leads to the least accuracy, which is 25.7% accuracy, and having positional encoding reconstruction loss leads to a higher accuracy, which is 33.6, indicating the role of positional encoding in modeling the latent space for subaction learning in complex activities. And as expected, having both of them leads to a better performance. And next, we include the contrastive loss in learning and then vary the reconstruction loss parameters. As it can be seen in the expected trend, having all three leads to the best performance. Now, let us look at some qualitative results. So, here we compare our method with the baseline CTE before Viterbi and after Viterbi. So, the rows with init indicate before Viterbi performance. So, by init we mean the initial predictions which are directly taken from the embedding, and the second and fourth row represent after Viterbi performance. So, if we compare the before Viterbi performance, that is CTE init and Rs init, we see that our model suffers from less jitter or less subaction transition compared to the baseline, where there is a heavy transition happening from one subaction to another, while in ground truth we do not see any such transitions happening. But after Viterbi refinement, the subaction jitters get reduced because of the strict enforcement of the state transition model, and we show that our method outperforms the state of the art in terms of the overall ordering as well as in terms of jitter. Here is another example to show our method before Viterbi and after Viterbi performance, and this is for an example where the person is performing make tea. Here we can show that whenever there is a subaction transition happening, that is from add tea bag to pour water, it tries to confuse with to stir tea or spoon sugar, where whenever there is a transition from one subaction to another, our model tries it experiences slight jitter in assignment of the latent concepts, but that we resolve with the help of Viterbi and state transition module. So, to conclude, we propose an end-to-end approach for subaction learning in complex activities in an unsupervised manner, and then design a latent space that incorporates visual as well as positional information together. And then we show that this sort of learning helps for robust representations that in itself is able to do a reasonable clustering of subactions. Thank you.